one graduate student who is working with looking at past historic outbreaks of mountain pine beetle right in the northern part of where mountain pine beetle's range has historically been. And this is an area that we expect the population to be most susceptible to climate change, because it's an area that's cold. It's around that -40 isotherm where we typically get very cold winters, which has in the past caused the beetle population to drop. So what she has done is use tree ring analysis, so the patterns that we see in incremental growth in trees, to be able to look back historically in time and identify when there were past outbreaks of mountain pine beetle. And then look at how those past outbreaks affect the forest as it currently is structured. And then also bring in the element of climate. How has climate historically affected these pine beetle outbreaks? We've used climate data from the Fort St. James research station, which goes back over 100 years, which is one of the longest records that we have in BC. So it's a great resource. But we're also able to use tree ring analysis to reconstruct climate. We've done a little bit of that as well. But collectively, what we hope to get out of this research is an ability to predict what might happen to mountain pine beetle populations as climate change continues on. Where do we expect to see mountain pine beetle being able to move into? What factors are most important in the northern part of its range for controlling the population? How important is species composition of host trees and non-host trees? All those kinds of things we're hoping to be able to provide some recommendations to forest managers for in the future. I also have a number of graduate students working on a foliar fungus that also attacks lodgepole pine, but it tends to attack the younger trees. It's called Dothostroma septosporum, or red band needle blight. And this fungus never tended to be a problem historically. We knew it was around in BC, but it never caused tree mortality, never was really much of a problem. However, around 1995, it started emerging as a very important destructive foliar pathogen, and we questioned why that was. Is it that the fungus all of a sudden developed a particular strain that was very virulent and much more able to attack its host? Or is it that the climate has become more conducive to the fungus's ability to spread? Or is it that forest management practices, which had been favoring development of pine plantations, have actually provided more host? So there was a bunch of questions that related to trying to figure out why this fungus, which never was a problem, all of a sudden started becoming a problem. We've used a variety of tools. We've used molecular biology approaches to look at the way that the fungus reproduces. Does it have a sexual stage and an asexual stage? The sexual stage would allow for genetic mixing, new strains of the fungus to pop up, and maybe one of those was particularly virulent. Does it spread mostly through the asexual conidia, it's called, which are splash dispersed in raindrops? The rains hit the foliage and the spore pops off. Or are they dispersed as a wind-borne sexual stage called an ascospore? So all of these were important questions about how the fungus spreads. So we've also used tree ring analysis to look at past outbreaks of this red band needle blight disease to see whether or not the fungus was causing outbreaks historically, or whether it really wasn't doing much of anything until very recently.